Hi from sunny California. I am going to stop the cat theme after this lecture. I want to start off where we left off last week. Recall that last week we took all the legal positions in the game Go and represented them as vertices and then developed a directed graph by moving from legal position to legal position. So it's not a legal move to legal move, but you're moving from one legal position to the other position. So the actual edges represented moves. Before I go back to the whole discussion of graphs, I wanted to go to something very specific that I've been asked by a lot of you, but how does one actually win at Go? Technically, the game ends when both players pass because there's no more profitable moves left. There might be moves left. For example, you could do a suicide, but that's not a profitable move. So at that point, when both participants or players agree that there is no more moves left, the game is scored. So the player with a greater number of controlled areas, for example, a controlled area could be that you have 4 corners all with your white stone, and now you control the area inside because black can't put theirs there. Some people also add in the number of captured stones and add in a handicap for starting second. The way we're going to score Go is at the end of the play, we're going to sum the number of empty points that your stones surround and the number of your stones on the board. Now, if you've captured more whites than whites have captured you, you will have more black stones on the board, for example. So this is how we're going to score the game. It's not universal. There seems to be so many variations of the game Go. I just had to pick one. So let's go back to the directed edges. So outgoing edges from a position is in a one-to-one correspondence with moves, as long as those moves are not single stone suicide. So this should make perfect sense because that's how you're developing the game graph. You're representing the game graph by taking all the legal moves and then drawing edges, illegal positions, and then drawing edges from one position to the other. What's a single stone suicide? Well, this is what I think a single stone suicide is. You have 4 whites in the center. If you put another white in the center of your own, that's a single stone suicide because you lose that white. If we had to prove this, what do we have to prove? Unusual here, I'm not going to prove this, but I'm going to have you think about what to prove because in a lot of your math classes you have to prove one-to-oneness. So what is it we need to prove here? Something is one-to-one. The intuitive definition is that you have a correspondence between each element in the domain gets mapped to one element in the range. So what is in the domain here? You're taking edges. So the actual arrow, and each arrow represents a move. And those moves can't be single stone suicides. So you're trying to actually find this one gets mapped to this one gets mapped to this one, and so forth. One direction is obviously easy. If I have an edge, then it's associated with a move because that's how I created it. What I don't want, what foils one-to-oneness, is I don't want this. You can think of the graph of y equals x squared, which is probably the most used and abused function in the undergraduate curriculum of mathematics. We have 2 different x values yielding one y value, so we don't want that. In other words, given one move I get from a configuration to configuration Q, this is the only way to get that move. Another way to say this is that the configuration Q is uniquely arrived at by P. Well, what about this? You can get to this particular configuration in 2 different ways. Well, this configuration is a single stone suicide, so it's not in regards here. What about these? Well, they're not the same move. They have to be the same move. These 2 are completely different moves. It's the moves that are in your range that you're mapping to. So I'm going to stop this module and we're going to move on to some other things. I'm not going to prove this, but I'm going to post something with the proof in it online so you can see the proof and review it. You asked me a lot about how do you prove things. One way is to watch a lot of proofs. So I think we're good at doing that as professors. We show you a lot of completed proofs. So reading a completed proof is one way to look at how to do proofs. But you can't do by just watching. You actually have to do by doing. And that's another way to learn things. And then you learn certain things, like what do I have to do when I prove something's one-to-one? When I prove something's one-to-one, this is what I'm trying to do. So you really have to map these things out. It requires a lot of patience and bravery.